Hi, chemistry students. This is Miss Fretz, and this is your lesson on periodic trends. You should take notes using provided guided notes or on your own in your chemistry notebook. So first of all, a quick review from previous lessons. What is the periodic law? And the periodic law states that when elements are arranged in order of increasing atomic number, their physical and chemical properties show a periodic pattern. And we're going to dive deeper into that periodic pattern this particular lesson as we talk about trends that we can see in the elements in the periodic table when they are arranged by increasing atomic number. And remember, atomic number are number of protons. And just to remind you, columns on the periodic table are sometimes called families or groups. And because they have the same number of valence electrons, families act and react in similar ways. And in a previous lesson, we talked about four groups that are actually really called families because they are so similar. The alkali metals, which are group 1, the alkaline earth metals, which are group 2, the halogens, which are group 17, and the noble gases that are group 18. But as we go across a period or down a column or group, we do see repeating trends, and that's what we're going to focus on in this lesson. So this lesson is appropriately called periodic trends, and we're going to talk about 4 different periodic trends that you can actually see and graph. As you can kind of see in this graph, we have trends for atomic radius, which we're going to define, and you'll notice that we have like down and down and downward trends, and we also see sort of upward trends in terms of these peaks. So not only are we going to define them this class, but next class you're actually going to do some graphs so that you can hopefully understand and use the periodic table to make predictions. First of all, we're going to write down the definition of what's called the atomic radius. This is trend number 1. And the definition of the atomic radius is the size of the atom. It's kind of a way of sizing up the atom, not by mass, but by actual physical size. The size of the atom from the nucleus to the edge of the electron cloud. You may know a radius as being in a circle from the middle of the circle to the outside edge. Well, if you think of the nucleus as the middle of the circle and the outside edge as being the edge of the electron cloud, this is a measure of that. Now, the trend in the radius is that radius decreases across a period. And that's because there's an increased positive charge of the nucleus, which makes the electrons move closer to the nucleus. And the radius increases down a group. And that's because each row on the periodic table adds a shell or energy level to the atom that is farther out. So if you've got an extra level, you're going to be farther out, you're going to be bigger. And we'll talk about that a little bit more. Now, I want you to actually see this so that you can kind of visualize this trend. Hopefully you've written down these things, but really focus on this right now so you can see the trend. So what this is, what these measurements are in something called picometers, which is very, very little measurement, is the size of the actual atom from the nucleus to the outside of the electron cloud. And you can see as we go across a period, now notice we don't have the transition metals in here, but essentially we're going across a period. This is period 1, so you can see hydrogen and then helium. You can see as you go from hydrogen to helium, the size goes from 37 to 31. So the atomic radius decreases. As you go from lithium to neon, the size goes from 152 all the way down to 71. As you go from sodium to argon, we go from 186 all the way down to 98. So you can see as you go across a period, the atom gets smaller. And the reason for this is we're adding to the same energy level. This is our first energy level, this is our second, this is our third. We're adding to the same area of space, the same level where the electrons are being added. However, the nucleus is getting to be more positively charged. And if we can remember, and why is it getting more positively charged? Because there are more protons in neon than there are in lithium. Neon has 10 protons in its nucleus. Lithium has only 3. And remember, the nucleus is a very, very small part of the overall atom. It's essentially a really powerful attraction right in the middle, but a dot, like a ladybug in a stadium. And the electrons are out in this cloud, and the neon nucleus with its 10 protons, which are positive, are very attractive to the electrons out in the electron cloud. Because there are 10 of them, they're putting out a positive charge that's worth 10 plus, whereas lithium only has 3 protons in its nucleus and is only putting out a charge of 3 plus. So in the second energy level, neon's electrons, even though there are more of them, are really attracted to those 10 positive protons, whereas lithium only has 3 protons and is not nearly as attractive. I mean, that's the reason for the trend. You do need to know the trend, but I always feel like it makes more sense if I understand, well, neon has more everything. Why isn't it bigger? Well, because we're talking about attraction to the nucleus, and the electrons are going to sort of squeeze in because the nucleus is so powerful. It's got that positive 10 charge of protons, whereas lithium only has a positive 3. And same thing for each one. Now, why does it get bigger, even though the nucleus also gets more positive? Why does it get bigger as we go down? Because energy levels have defined limits. The second energy level is definitely going to be smaller than the third energy level. They can't jump each other. So if you're going and adding more and more energy levels, or that's why we sort of think of them as shells, you're definitely going to get bigger. So as you go down, you're going to have this hydrogen only has 1 energy level, 1s. Lithium has 2 energy levels. Sodium has 3s, 4s, 5s. So just because you have more energy levels, you get bigger. All right, so you can kind of see, if you can kind of visualize this, you can see that as you go across, the size decreases, the atomic radius being a measure of the size, and as you go down, the size increases, and again, because we've got a more powerful nucleus drawing the electrons closer as we go across, but that's negated when we go down because there are just more energy levels. And so again, the trend is the atomic radius decreases going across, but increases going down. So let's just try a question like you might see on the SOL. Which would be the largest atom? And that by largest atom, we mean the one with the largest radius, not the largest weight, the largest radius. Now look at your periodic table, hopefully you have that, and decide which would be have the largest radius. And again, remember, these are all in the same period. So which one is the least attractive? Circle. You should have circled lithium, because lithium, if you remember the trend, lithium is all the way to the left. So it is going to be the one with the least attraction to those electrons in the second energy level, so it's going to be the biggest. Fluorine, actually, of these 3 is going to be the smallest because it has 9 protons. Now, which is going to be the smallest? This is going down the alkali metals, lithium, sodium, potassium, and cesium. And the hint is lithium only has 2 energy levels. Sodium has 3, potassium has 4, cesium has 5. So which is going to have the smallest radius? And again, this time you're going to say lithium again. Okay, so that's trend 1. That's the size. Let's talk about 3 more trends. The next, okay, so again, one more time, atomic radius decreases going across, and it increases going down. And I had a student who told me this who came up with this idea of to the right is tight. So this is the highest and the rightest. Helium here is the smallest on the periodic table. To the right is tight, to the left is loose. That means down here at francium, it's going to be the largest on the periodic table because to the left is loose, and therefore it's going to be bigger. All right, so next trend is first ionization energy. Now, ionization energy is not the energy to make an ion. It's the energy required to make a 1+ ion. So the definition is the energy required to remove an electron from an atom, whether it wants to be removed or not. It's the energy to make it a 1+ ion. Now, the trend for this is it tends to increase across a period. Because of that increased nuclear charge, makes it harder to remove. And it tends to decrease down a group because the outer electrons are farther away from the nucleus and easier to remove. So this is kind of the general graph of the trend, and you can see going across, going from the second period from lithium to neon, we're generally going up. We're not going to worry about these bumps. We're generally going up, but going down a family like helium, neon, and argon, that's the noble gases, you can see the ionization energy go down. Now you can see the bumps are here when you're adding to the P sublevel. But that's kind of an intensified thing. Don't worry about it. The general trend is as you go across a period, ionization energy goes up. As you go down a family or down a group, ionization energy goes down. Okay, and this is a little graph that actually has the ionization energies. So if you can read it kind of roughly, you can see that you go across. The ionization energy for lithium is just 520, whereas the ionization energy for neon is 2000. So you're going to increase. When you're going down, you can see lithium is 520, but as you go down, francium here or cesium is 375, so it decreases. Again, ionization energy increases this way, decreases this way. And again, the reason these tighter atoms over here to the right is tight because they have a lot of protons attracting electrons, will not give up their electron easily. And that's what ionization energy is, the energy to take away an electron. On the other hand, going down, they're more loosely held because they're further out from the nucleus, and so they're easier to take off. Okay, so let's try another one. Which has the greatest ionization energy? And this is the halogens going down the family. Which one is most loosely held? Which one is furthest away from the nucleus, therefore easiest to remove the valence electron? We're trying to take away that first valence electron. And again, the one that has the greatest ionization energy, or the one that's hardest to remove, is going to be fluorine. The one that's easiest to remove would be iodine because it's furthest away. Fluorine is going to be the hardest to remove because it has its valence electrons closer to the nucleus. Okay, which has the least ionization energy? And you got to look. These are all in period 3, but which one is holding on the least? Which one is the biggest, is the loosest of all of these? And you should have gotten aluminum. Okay, it's the one that has, of all of these particular elements in period 3, it's the one that has the least protons and therefore is the least attractive to those electrons out in the cloud. Okay, let's do the next one. All right, so again, ionization energy increases going across and decreases going down. All right, electronegativity. This is the third trend. It's a measure of the ability of an atom in a chemical compound to attract electrons. So it's kind of like ionization energy, but it's kind of not. It is saying, how easy is it for me to attract something negative? And again, you got to think of the fact that if you have a real positive nucleus or a real small number of energy levels, you're going to be able to attract an electron much more easily to your electron cloud using your nucleus. So the trend is electronegativity tends to increase across a period because of the more positive nuclear charge increases the attraction, and electronegativity tends to decrease down a group because they're further out from the nucleus. Now there's one exception to this. Noble gases have no electronegativity because they have full outer energy levels. Remember, we're trying to attract electrons into a chemical compound, into our energy levels. And noble gases really don't have any room for extra electrons. So this trend is the same as ionization energy, except we exclude the noble gases, which means that the most electronegative element on the periodic table is fluorine. This is a table of electronegativities, and they're measured in something called Paulings. And you can see fluorine here up at the right, because the right is tight. Has the highest electronegativity. It's the most attractive. It just needs one more valence electron, and plus it's very small and powerful in terms of its nucleus, and so it is the most electronegative element on the periodic table. And francium over here, left is loose, is the largest, attracting it the furthest out in that 7th energy level, so it has the smallest electronegativity. Notice the noble gases are not on this at all, all because they don't have any place to attract the electrons to. Their outer energy levels are full. So again, electronegativity increases, except this is the end. This is to the right is tight. So fluorine has the highest electronegativity, and francium has the smallest electronegativity. Okay, so which has the greatest? Oxygen, nitrogen, or carbon? Look at your periodic table. Which one is most to the right? Remember, to the right is tight. To the right is most attractive. And right, oxygen is right next to fluorine, and we know that fluorine has the greatest electronegativity. Okay, so electronegativity increases across and decreases down. Finally, last trend. Okay, so here's our summary of these first three trends, and they're kind of interrelated. So atomic radius decreases, ionization energy increases, and electronegativity increases as you go across a period. As you go down, atomic radius increases, ionization energy decreases, and electronegativity decreases. Remember, to the right is tight. So you're going to be small if you're helium. You're going to hold on to that electron that you want to take off with ionization energy really hard. So to the right is tight. Helium has the smallest atomic radius and the largest ionization energy. Remember electronegativity's definition. You have to attract an electron. There's no room in helium, so we exclude the noble gases, and fluorine would have the greatest electronegativity. To the left is loose, so this is an easy one. Francium, or francium sometimes they call it, has the biggest atomic radius because it's loosely held. It's really far out. Ionization energy is the smallest because it's loosely held. To the left is loose. And electronegativity is the smallest because it's loose. It's not attracting electrons. Last trend, though, is something called shielding effect. Shielding occurs when the inner electrons in an atom shield the outer electrons from the full charge of the nucleus. Keep in mind that this phenomenon is only important as you move down the periodic table. Again, remember, we're adding electrons to the same energy level, and really shielding just says how many energy levels are between me and the nucleus. So that's constant. So if either hydrogen or helium have no energy levels between it and the nucleus, lithium all the way through neon have one energy level between it and the nucleus. Its valence electrons are being added to the second energy level. The third period, all from sodium to argon, we're always adding to the third energy level, so we always have two energy levels that are full between us and the nucleus. That's why the shielding effect stays constant across. As we go down, though, we keep adding energy levels, so it increases. All right, so what is true about the shielding effect of chlorine versus sodium? They are in the same period, okay? They're both in the third energy level, the third period. So their shielding effect is the same. On the other hand, what's true about the shielding effect of chlorine versus iodine? Chlorine is in the third energy level. Iodine is, I believe, in the fifth. So in between its valence electrons and the nucleus, iodine's going to have more. So iodine has the greater shield. Now we're going to go over this a lot more in a lab where you're going to do some graphing, but that is your lesson on periodic trends.